Hello, everybody. I'm Sebastian Heller, the Doctoral Studies Liaison. I'm afraid my camera isn't working today. I'll be doing the Q&A with you. Dr. Stavros Dragoshis is the one who's prepared this webinar. We will be playing a video of the actual seminar, and then we're going to follow it with a Q&A, which Dr. Stavros Dragoshis will present in person. I'll pass you over to Dr. Stavros to say hello, and then we'll proceed with the video. Dr. Stavros?
Hi to everyone. Welcome to this webinar about sampling distributions and t-test. This was recorded recently and it will be played now. And after that, you can ask your questions. I will be very happy to answer them and have a chat with you about anything that might concern you related with this webinar. So whenever you are ready, Sebastian.
We're just going to share the screen and we'll be ready. Don't forget to put any questions that you have in the Q&A section, which you can find it at the bottom of your Zoom screen. Two icons to the left from the green share screen button, or two icons from the right. So it's near the left-hand side. It's Q&A, it's two speech bubbles. Thank you very much.
Hello, this is a lecture, a webinar on sampling distributions and statistical inferences. I think it's the third one in a series of lectures on statistical related themes or topics. So I took that into consideration when I was making up this one, because I think the students are supposed to learn about some things in previous webinars, like the mean and standard deviation and some basic meanings, some basic statistical related definitions and so let's start with today's lecture. If I manage to, well, I'm not really familiar with Zoom. So today we will be talking about distributions, and the most important distribution in parametric statistics, which is a normal distribution, and t-test. So these are the two major themes of today's webinar. But throughout the lecture, we will come across normal distributions, standard normal distributions, the central limit theorem, probability density functions, null hypothesis significance testing, or NHST for short. And we will see three types of t-tests: the one sample t-test, independent sample t-test, independent samples t-test, and paired samples t-test. And we will also have a look at p-values throughout the webinar. So what is a distribution? We have many types of distributions in statistics, and they describe a range of values that are either directly observed or those values are described in terms of probabilities, even if we haven't really observed them. And this is specifically about probability and density functions and other related functions that can provide distributions on indirectly, so without directly observing something, without measuring directly something. And here is just a good way to to understand distributions is to think about the measurement, let's say the height or the weight of 10 people in a classroom. We measure their height. This is a measurement in numbers. So this is it's either interval. It's an interval scale, and we lay these numbers down from the smallest to the biggest number. So we will start by writing these numbers down from the smallest number to the biggest number, and we will only write down the unique numbers. So if two people in our sample have the same height, we will write down only one of them, and we will stack on top of these numbers how many times we came across it. What is the frequency of observing a height? So this is basically what a distribution is. The measurement of some sort of measurement, and we write down something related to this measure. The most let's say simple way to describe a measurement is to write down the frequency of each value of a measurement. And this is frequency distributions. And one of such distribution is the normal distribution. So a normal distribution, if we measure something and has some properties to it, some specific properties, then it's called a normal distribution. The normal distributions have specific properties, and the most distinctive one, it's a bell-shaped curve. So when we plot on a graph the frequency of each unique value of a measurement and the shape of this frequency distribution resembles a bell, then this is one property of a normal distribution. A bell-shaped curve means that data are symmetrically distributed, and specifically this means that most values are clustered in the center of the distribution, where the peak of the bell is located. We have the most value, the most frequent. Our most frequent observation is in the middle of the distribution of the range of values from the smallest to the biggest. In the middle, we have the middle number of a measurement, and the middle number is most commonly observed, most frequently observed. And this also means that the mean, the median, and the mode are the same in normal distributions that are perfectly normal. Left and right from the center, we have half the values that are left and half the values that are right from the center. So half the values are below the mean and half the values are above the mean. Same with the median, same with the mode. And I assume that you know this these terms from the previous lecture of this series. Another thing that is really important for normal distributions is that the density, so how frequent we see an observation, tapers off, so it becomes less frequent as you move away from the center, either to the left, either to the right. if you start to move from the center of the distribution to the two ends, so towards the smallest number or towards the biggest number, density or frequency tapers off or becomes less uh, and less frequent or dense. And the way to move away from the center, so let's say how to scale the distance from the center, we use the standard deviation, which again, I assume that you learned from the previous lecture, what it is. So the standard deviation is a way to move away from the center towards the two ends of the distribution, towards the smallest number or towards the biggest number. This is the way to move away from the center in standard deviation units. And it has been called, the standard deviation has been called, it's like a yardstick. It's how you measure distance. It's like a ruler or some sort of measuring distance from the center towards the two ends of the distribution. Now we will have a look at an example with real data that I gathered from the internet. So we'll see the age of celebrities. I don't know if you know these people here. I knew most of them except from this one and this one. And I don't remember the name of this one either. But this is Kim Jong-un. This is Beyonce. I think I'm not sure if you can see my mouse, but this is Kim Jong-un, Beyonce, Macron. What's your name? Shakira, I think. Nicki Minaj. This is Arwen from The Lord of the Rings. Frodo, Orlando Bloom, Angelina Jolie, Eminem, Elon Musk, and Mike Tyson, yeah. Cristiano Ronaldo, Barack Obama, Michael Jordan, and Greta Thunberg. I don't know who this, I don't remember her name. I don't remember the name of this thing. Anyway, we can see the age of, let's say, celebrities that most of us can recognize. And we can say something from this data that I have here. Probably there are other samples, but from this one, we can see that most people that are celebrities are within their 40s. We can also say something about gender and age as we move away from the center. But so we expect that the middle of the distribution will be something around 40. And as we move away from the center towards the smallest or the biggest values, density of the distribution will fall, will become less dense, then will taper off. And this is exactly what happens if we plot this data. We have a mean age of 43.6 years of age, which is around here. And we see that most values are in the center. We have a standard deviation of 10.9 years, a median age of 46, and immediately we start to think that maybe this is not a perfectly normal distribution because the mean and the median are not the same. And this is because we have three modes. We have one mode that is 41 years of age, one mode that is 46, and one mode that is 47. So this is a multimodal distribution. It's not a perfectly normal distribution, and this becomes apparent if we move away from the center 2 or 3 standard deviations. But we see here, for example, that we have 2 celebrities that are 41 years old. We have 2 celebrities that are 46, and 2 celebrities that are 47. So that's why we get this multimodal distribution, but it has some resemblance, or it has some characteristics of a normal distribution. It's not perfectly normal, but we see that most values are located in the center. And as we move away from the center, we see that density tapers off, and density is what I have plotted here. Right, okay, so as we have been discussing so far, a normal distribution can be described by 2 values, the mean and a standard deviation. If we know that something has a measurement, when I talk about something, I mean a measurement. If we know that a measurement has a perfectly normal distribution, we can describe it with using only 2 parameters, 2 values, the mean and the standard deviation. The mean shows us where the peak is, where most values lie, where the most frequent value is. And if we have different samples of the same measurement, and we have different means, we can see that increasing the mean moves the curve right. So the whole curve of the bell-shaped curve will move to the right. If we decrease the mean, then this curve will move to the left. So we can say that the mean is a location parameter. For the standard deviation, well, the standard deviation shows the dispersion of values around the mean. So how it's a measurement of how the values are tapering off as we move away from the mean. So again, in the same measurement, if we find different means and different standard deviations in different samples, but we still have a normal distribution, by changing the standard deviation, the curve will be stretched or squeezed. So a small standard deviation will narrow the curve. If we have a large standard deviation, then we will have a wide curve. So we can say that the standard deviation is a scale parameter. It's scaling the curve. So the shape of a graph is changing based on the mean or the standard deviation. And here are some examples from a measurement that is called SAT, Scholastic something test. It's something that they used in the United States to apply for universities to study, for studying in a university. I'm not exactly sure what it is, but it's something that students, it's an exam that it's a test that the students must pass before they apply to study at universities in the United States. And these tests have a fairly standard normal distribution. They have a mean of around 1,000 and a standard deviation of around 150. But in different samples, so let's say in different areas of the United States or in different schools, in different samples, this changes a little bit. And here we have on the left side here of the graph, we have collected, let's say, 3 samples from 3 different areas. We have the same mean. We have, let's say, a mean of 1,000 SAT score. And but the standard deviation is different in these 3 samples. So we can see that the curve is becoming more narrow or more wide, depending on the standard deviation. And on the other side, we have the same standard deviation on 3 samples, but we have 3 different means. And these means move the curve along the axis. So they position the curve on different locations in the distribution. So that's why the mean is a location parameter and the standard deviation, it's a scaling parameter. And we can describe normal distributions only with these 2 parameters. Now, standard normal distributions are so important because they have been observed in many measurements, in many variables that scientists have measured. And because they were seen in so many different data, many statistical tests are designed to work with normally distributed variables. IQ is one measurement that has a normal distribution. The mean is around 100 and the standard deviation is around 15 IQ points. Height, as I said before, throwing of 2 dice has a normal distribution with a mean of 7. So the most commonly observed value is 7. As we move away from the center, this is the other numbers are seen less often. Here are the probabilities. Birth weight is normally distributed, and many class measurements like performance of different sorts and are also normally distributed. Most people are mid performance. We have some that are high performance and others that are low performance. Yeah, so normal distributions are almost everywhere. And they have some very specific properties, like we said before, with that can be described with a location parameter and a scaling parameter. And if they are perfectly normal, we observe some merge of the location parameters like the mean, the median, and the mode. They are all the same. And we saw some different properties of this distribution. So because all of this shows us that the normal distributions are symmetrical. And because of this, we know exactly what percentages of values fall in each area of under this bell-shaped curve. First of all, we know the area that is under the bell-shaped curve. This is the proportion of area that is under the bell-shaped curve is exactly 1. And if this is sliced by the standard deviation as a yardstick, we get different proportions of density of how frequently we observe values. And this is again because of the symmetrical nature of the bell-shaped curve. If we move away from the center in standard deviation units, we cover different amount of area of different proportion of area under this bell-shaped curve. And there is something that is called the empirical rule that says that if we move one standard deviation away from the mean, so one standard deviation to the left and one to the right, we have 68% of area covered. So 68% of values fall one standard deviation above or below the mean. If we move two standard deviations from the mean, we cover 95% of the area that is under the bell-shaped curve. And if we move three standard deviation away from the mean, we cover this number here, which is 99.7% of the area is covered under the bell-shaped curve. And I explained this here. So again, because of the symmetrical properties of the normal distribution, we know exactly how much area, what is the proportion of area that is covered while we move from the center of the bell-shaped curve in units of standard deviation. And that's if we have a perfectly normal distribution. This rule always applies. And here I show you again the SAT scores, but it's the same with other measurements as well, like IQ. As I said before, the standard deviation is 150 units of this measurement of SAT scores. And in this sample here, the mean is 1,150 SAT score. And if we move one standard deviation above and one standard deviation below the mean, 68% of the values fall here. 34 on that side and 34 on that side. If we move two standard deviations from the mean, we cover 95% of values. This is a 68% that is covered in one standard deviation above and below the mean, plus 13.5% of area that is covered two standard deviations away from the mean. And that's because we have this tapering off of the frequency of observed values as we move away from the center. And if we move three standard deviations away from the mean, 99.7% of the values are here. So we have still some values outside. We have some extreme values here, but we cover almost all the area of that is under this bell-shaped curve. Similarly, here with our celebrities, we know that the mean age is 43.6. So the mean celebrity age is this one. The standard deviation is 10.9 years of age. So if we subtract this value from the mean, we get the lower limit of age that will fall within one standard deviation from the mean. And if we add this value to the mean, we get the upper limit, and anything below this value will fall within one standard deviation from the mean. And we get 68% of our sample. We had 19 celebrities. So 12 of these, not exactly 13, will be here. And we have these celebrities that are one standard deviation from the mean age. So 68% of them are one standard deviation away from the mean, above or below. And these are the lower limit and the upper limit of age that basically cut the bell-shaped curve into into these 68% of values. Right. So because of the usefulness of these symmetrical properties of the normal distributions, they were extensively studied. And there is a theorem that describes some of their properties. And it's really useful for us that we are doing research with samples. This theorem, it's called the central limit theorem. And basically says that if we take small samples to describe a population, this is exactly what we do in research. We rarely can measure, if not never, we take small samples to describe a population. If we are talking about the SAT measurements that I showed before, we might take a few samples from some institutions to describe the whole population of examinees who want to proceed to study in universities. The central limit theorem basically says that even if a sample mean, the sample distribution is not normal, the means of many samples will be normally distributed. Right, so if I take SAT scores from here in Cyprus that are not, basically this SAT scores don't exist here in Cyprus, but if I take some people and bring the SAT test to Cyprus and measure their responses, maybe the distribution of the Cyprus sample will not be normally distributed. But if I take many samples, let's say from countries outside the United States, and I take the means of each of these samples and I plot them, I will have a normal distribution. But that also means that if I have a bigger sample, therefore if I pull together all these samples and plot them, I will get a normal distribution. So the bigger the sample, the more likely you will get a normal distribution of a measure. And this is basically the holy grail of parametric statistics, which are based on this theorem. The parametric statistics are based on the normal distribution and all its properties. And what we are going to learn today, like the t-test and all of that, these are fairly parametric. Another thing that comes out of the properties of normal distributions are the PDFs, probability density functions. It's the idea that you can get a probability of a number, so how frequently a number can be observed, that you haven't measured. So if I measure from 10 people their IQs, which is a measurement that I know it's normally distributed, and from in these 10 values, I don't have the number 150, let's say. I can find the probability of obtaining this number that I didn't measure in the population by using this function here. This is the probability density function. And this function can be used only if the distribution of the measurement is normal. We can check if our measurement is normal by using QQ plot or some other specialized test that examine what is the if our distribution approaches a normal distribution or any other distribution in this case. But I will not go into them. And if this is the case, then we can fit a probability density function into our data. It takes only 2 parameters. And as we've seen before, these 2 parameters are the mean and the standard deviation. And it passes them through this equation here. It looks complicated, but it's not. We are not going to go over this, but you solve this one first. You get a minus number multiplied by this constant here. And then you solve this one and multiply with the result of the equation to the right. And you get a probability of obtaining this number that you haven't directly observed. We can solve this. You can use this this link here to visit a website where this probability density function is exists, and you can play around with it. You can throw numbers in it and see what is the probability of them occurring. Or you can solve it by hand if you know for IQ, let's say that we know the mean 100 and the standard deviation is 15. You can solve for an IQ of 150 as I did. And the p-value of obtaining an IQ of 150 is this here. So the probability value of seeing this measurement is 0.1%. Yeah, so that's about probability density functions. The bottom line is that you can find the probability of getting a value that you haven't directly observed. So another way to think about normal distribution is the standard normal distribution, where the mean is 0 and the standard deviation is 1. If it's a mistake here, it should say 1. To get a standard normal distribution, we first need to transform the values to z-scores, and z-scores tells you how many standard deviations away from the mean each value lies. We can transform normal distributions to standard normal distributions for several reasons, like to find the probability of observations in a distribution falling above or below a given value, to find the probability that a sample mean is significantly different from a known population mean, or to compare scores of different distributions on different measurements that have different means and standard deviations, but we can compare their Z values. And this is a Z-score formula. Basically, from each value, we subtract the mean and we divide this by the standard deviation. Again, we are solving for IQ here. For IQ, for IQ 150, we do 150 minus 100. And the result is divided by the standard deviation. And we get this number here. So IQ 150 is 3.33 standard deviation above the mean. And we can do one more for IQ 80. And IQ 80 is 1.33 standard deviations below the mean. Right? I hope this is clear. And here are two distributions with IQs that I made up. These are not real measurements. This is 10,000 cases here. We see that the raw IQ scores, we see that the tip of the curve here is around 100 and the standard deviation is 15. And if we convert these values to z-scores, we see that the standard deviation is 0 because these values are 0 standard deviation away from the mean. It's the same thing, right? But if we move away, we have 1 standard deviation away from the mean, 2 standard deviation away from the mean, 3, and so on. So standard normal distributions is a normal distribution that is converted to z-score, and then what we plot here is the how far away each value is from the mean in units of standard deviation. The z-scores are the units of standard deviations away from the mean. So because standard normal distributions are even more symmetric than real normal distributions, we have the probability of occurrence of every possible z-score, and we have tables for this. So each z-score comes with an associated probability of occurrence. Each z-score has a p-value. These are standard p-values and exist for both positive and negative z-scores. And they look something like this. This is the probability of occurrence of every z-score that is negative, so it's below the mean. And we can see, for example, what is the probability of occurrence of IQ80, which has a z-score of minus 1.33. And we go here and we find minus 1.33, and we do this mapping here, and we get this value, which is 0.9, and if we convert this to percentage, we say that the probability of occurrence is 9%. Now, it's again this idea that we need to find the proportion of area that is covered below the curve, but in this instance, we always move from the left to the right. And I'm saying this because if we solve for IQ 150, which has a z-score of 3.33, and its associated probability of occurrence, we go here and we write 3.33, and we do the mapping for another 3, so it's 0.33. We find that the area that is covered until we reach this z-score is this huge number here with 0.9999 something. Right, so the area that is covered from left to right is this, but the probability of occurrence of this number or higher, because this is how we think about these things, it's what is left, because it's a positive number. So the probability of occurrence of this of IQ 150 and the z-score of 3.33, it's 0.43. So it's not face value, the number that we get from this probability table, because we move from left to right, because the equation of the probability density function that we seen before that has this incremental in the nature of the Euler number, I think, anyway. So this is what is happening here. If we have a negative value and we want to find the probability of occurrence of a negative z-score, we find it from this table, and because we want to know what is the probability of occurrence of this value or more extreme, meaning negatively more extreme, its face value, the proportion that it's taken by this z-score. But if it's a positive z-score, it's the remaining. So we need to take this value and subtract it from 100 or 1, the value of 1, in order to find the area that is left. So I hope this makes sense. And anyway, the take-home message for the lecture so far about normal distributions is that if we have a normal distribution, we can make standardized predictions about the probability of obtaining a specific value. Another important thing in statistics is the null hypothesis significance testing, or basically how to run research, how to turn research questions into hypotheses that can be tested with data. So far, we saw how to describe a sample with a mean and a standard deviation. If the data is symmetrical or they are normal or they resemble a bell-shaped curve and it has these properties that we are discussing, then we can even make predictions about what is the probability of occurrence of a value that we have not yet measured. But we cannot test a complex research question with just the usage of distributions and z-score. Some complex research questions and can be, for example, what is it? Is treatment A better than treatment B at killing cancer cells? Is this advertising strategy more efficient than the other? Does this teaching method result in better grades than the other? Yeah, so to do this, we need to use some extra thinking. We need to include some things in our statistical calculation, but we also need to have a framework of thinking that takes into account some things that we haven't yet learned. But we will start with the definitions, of course. So we are looking at the null hypothesis significance testing, and we want to see what null hypothesis means first. This way of thinking, it's a combination of two different ways of thinking of how to use data to test hypotheses. One is the idea to compute probabilities, as we've seen so far, is how likely is something happening given the data, and the idea of competing hypotheses. So we need to have a baseline and a research hypothesis. So basically, we need to have more than one hypothesis. We need to have our research hypothesis and a baseline hypothesis. And often you will see that you have multiple research hypotheses, but you need to have a baseline to test it against. Right. And so this was probably first formalized by this guy here, where is Sir Ronald Fisher, Sir Ronald Fisher, who was working at UCL. And anyway, he once met a woman who said that he knows if milk was added first to tea, or if tea was added first and then milk. So this is England, so I guess tea is a very important part of everyday life. And he decided to test this and prepare 6 cups of tea, 3 with milk first and 3 with tea first. And 6 cups of tea have 20 different orders of presentation. But the woman had only one chance to get this correct. So 1 in 20, she had 5% chance of having a correct guess due to chance. Right? So if these were only 2 cups, the woman will have 50% chance of finding the correct order due to chance. But because this is 6 cups, the woman only had 5% chance of correctly guessing due to chance or luck alone. And Fisher thought that 5% chance of getting the result, of getting the correct answer randomly by luck is adequate to say that the woman indeed knows if milk was added first or tea was added first and then milk. So he thought 5% chance is okay to make it. And this 5% chance is important for us to understand that it's attached to the idea that the woman will make a lucky guess. So this is our level of acceptance. It's called the alpha level. So we give here 5, and again, if these were 2 cups, there will be 50% chance of getting it right by luck. But because it's 6 cups, there are 20 orders of presentation and only 1 guess. This is 5% chance of getting the correct guess by luck. And 5% chance we felt is adequate, or at least Fisher did, and then it became, the standard. So our level of acceptance is called the alpha level. And formally, the alpha level is the level of probability at which the null hypothesis is rejected. And then in social sciences, we usually set the alpha level to 5%. And that's probably because of Ronald Fisher here. So what is a null hypothesis? A null hypothesis is a statement of no difference, of no association, of no treatment effects. An alternative hypothesis is a statement of difference, of association, of treatment effects. So the first step in this NHST process is to transform the research question into null hypothesis and alternative hypothesis, and they are denoted like this, H0 and H1. The null hypothesis is always true until proven otherwise, and the H1 is a research hypothesis that we hope to adopt. And we only adopt it if we have enough evidence to drop the null hypothesis. And this if we get the probability of occurrence for the null hypothesis to be below our alpha level. So what we observe is because of the null hypothesis, and this probability of the null hypothesis producing the result is below our acceptance rate, right? To do this, we use p-values. We saw p-values extensively so far. So p-values in the NHST context let us know if the probability of observing a test statistic given the null hypothesis. The smaller the p-value, then better, because the less is the chance that the statistic is produced by the null hypothesis, right? Similarly, with a lady who can guess the milk, if the milk was added first, it's only 5% chance, and this is what we usually use for psychology or for the social sciences in general. Some research questions and their null hypotheses are presented here. So are teens better at math than adults? And the null hypothesis, so the hypothesis of no difference will be age has no effect on mathematical ability. Does taking aspirin every day reduce the chance of having a heart attack? Taking aspirin daily does not affect heart attack risk. Do teens use cell phones to access the internet more than others? Age has no effect on how cell phones are used for internet access. Do cats care about the colors of their food? cats express no food preferences based on color. Does chewing willow bark relieve pain? There's no difference in pain relief after chewing willow bark versus taking a placebo. Right, so we always need to have a baseline at which to compare our research hypothesis against, and we drop our baseline hypothesis if we have a low probability of occurrence for that. And let's see some examples using a real statistical test, and we will talk about 3 types of t-tests. So if we want to test something, a complex, as we name them, research question, and here we are talking about differences mostly. Let's say I want to compare the IQ between a sample of neurotypical individuals and a sample of individuals that are diagnosed with autism. I can measure IQ in these 2 groups and then just see which one has the biggest or the lowest average, if they are different or if they are the same. And say, for example, individuals with IQ have higher, individuals with autism have a higher IQ than neurotypical individuals. But this is not entirely correct because it's only tailored to the sample. What we really want to do is to make inferences about the populations at which the samples were collected. We want to say with some degree of certainty whether our results hold in individuals that we have not measured, but fill the characteristics of the sample. They are from the same population, right? And in order to do this, we need to take into account other things like how big is the sample, what is the standard deviation, or a combination of these 2 ideas, which is the standard error that we will look in a minute. So the t-test behind the scenes basically is here says what I have just told you. We can compare means from samples that we have collected, but we also want to see if the means will be different in different samples that we have not collected, basically in the population. And we can only say this if the standard error is small. Then the means we collected will not vary a lot in different samples that we have not collected. And if the standard error is large, and then there will be a lot of variation in other means that from samples that we have not collected. So if there are differences in our means and the standard error is small, then it means that the samples come indeed from different populations and have different characteristics, these populations, in our measurements. If we are measuring IQ, then we can say these populations have a different IQ. Oh, but sorry about this. If the standard error is large, then we just happen to have sample means that are different, but not guarantee that we will find the difference again, right? So so basically it comes down to this: the larger the differences between our samples relative to a standard error, the more likely the difference is true. It holds in other samples that we have not yet measured. And this, depending on the research question or the research where the differences are coming from, you can say that your experimental manipulation worked, or in clinical settings, you can say that there is or there is not a true difference in IQ in autism and control, right? So what is the standard error? the standard error is analogous to the standard deviation. The standard error tells us the spread in our sample values. The standard deviation tells us the spread of our sample values from our sample mean. The standard error tells us how far our sample mean is from the true mean of the population. It is an estimate, it's not a measurement. There's no way we can measure this unless we have access to the population. And it tells us the dispersion of the mean. It's useful in inductive statistics where we use a sample rather than the entire population. It gives smaller values as you increase the sample, so a smaller distance from the true mean. Right, so this basically it's an estimate of how far our mean is from the population mean, because we take our mean from a sample and not the population. And it's a mathematical equation that it always holds true if we have a perfectly normal distribution that is coming from a population that also has a perfectly normal distribution. And here, basically, what we do is we take a standard deviation and we divide it by the square root of the sample. This is how many individuals I have in the sample. So the first kind of t-test that we will look at is one sample t-test. And it's this equation here. It's our sample mean minus the population mean divided by the standard error. And we use this when we want to know whether our samples come from a particular population, but we don't have full population information available to us. For instance, we may want to know if a particular sample of college students is similar or different from college students in general. And here I will again go back to the SAT scores. If we collect SAT scores from Cyprus, then we want to compare it we want to compare it to the SAT scores in the United States. We can take the mean from the SAT scores that we gather from the Cyprus sample and compare it with the general SAT mean that they have in the United States in so many years that they are doing this SAT test. And so we can use this. In truth, we can use any value that we want here, hypothesized or the real one from population or not. And this is a formula that is also used inside other statistical tests. And we can also use it with small sample sizes. If we run a pilot study and we want to compare it to, let's say, a previous larger study, we can use this. It's the idea that we compare a mean from one sample, hence the name, one sample t-test, with a value. And this value theoretically needs to be the population mean, but in practice, this has many other uses. And we get a resulting t value that has a probability of occurrence, and whether the research question is directional or non-directional, we get this one-tail or two-tail test for our research question. And we need another parameter here, which is the degrees of freedom. The degrees of freedom is basically sample size -1 for our purposes here. And we will have a look at this later on more specifically. But let's say I have one sample of 25 individuals, then the degrees of freedom will be 24. And if my question is the SAT score of Cyprus larger or let's say higher than that of the United States, and I get a value that is 2.4, I get this number, and the probability of occurrence of this number by chance due to a null hypothesis that there's no difference or that the means are similar in our general population is 0.1 or 1%, which is less than 5%. That is our alpha level. And we will look at that again later. So there is another t-test. It's called the independent sample t-test. And it's this equation here, but it's basically a mean from one sample minus the mean from the other sample. This is the standard error of one mean and the standard error of another mean added together and then getting the square root of it. Independent sample t-test is used to compare the means of two groups of sample. It helps evaluate if the means of the two sets of data are statistically significantly different from each other. So that means do my two groups come from different populations? If there is difference in these two samples, we can say with some degree of certainty that these groups come from different populations. And we can say this because we are using the standard error as previously. Here we use the standard error, to see if the difference is small relative to the standard error. So, and this theoretically and because of the theorem that we examined before, basically it says that the difference we will find the difference again in other samples from the same populations. And here we again have this critical table. If we get a t-value at the end, this is for two-tailed hypotheses. So hypotheses that are non-directional, like if we have this example, let's say I have one group of students who take the SAT scores in Cyprus and another group of students who take the SAT scores in Cyprus. But let's say one of them is only males and the other is only female. And my question is, are there any difference between these two groups? So it's a non-directional hypothesis. It doesn't say if one group will perform better or worse than the other. We name these hypotheses two-tailed hypothesis. And we get the associated t-value and then degrees of freedom. That's why we want same number of participants in each group, so we have the same degrees of freedom. Otherwise, we pull them together using some mathematical equations, and we see the associated p-value. So what is the occurrence of this statistical value if the null hypothesis was true? Another t-test is a pair sample t-test, which basically means that we have the same sample in two different times, in two different occasions. So let's say 1 week apart. I measure the SAT scores in Cyprus today, and then I measure it in 1 week. I will use the pair sample t-test, which is one group, the same group tested 2 times, 2 different times. And the pair sample t-test gives a hypothesis examination of the difference between population means for a set of random samples with in a before and after situation or with subjects as like possible. So the pair t-test tests that the differences between the two observations are 0. If the differences are more than 0, then we get a high t-value. We will look at this equation in more detail later in this lecture, but basically, if you have one measurement today and then another in 1 week, then you get a difference, so you subtract one from the other, and then you sum the differences, and then here there's some trick here where you get the sum of the differences squared and the sum of differences squared, with something to be careful when you do this by hand, but there are a lot of software doing it anyway. So we get, and again, this has an accompanied critical table that again uses the degrees of freedom and it gives you the probability of seeing the t-test, which is a composite of the differences after taking into account the standard error, or in this case, the sum of differences. And in this way, you can say something about the population. So some information about these critical tables that have the associated p-values of each t-test. So each critical table for a t-test is a frequency table. It represents the frequency of having a p-value based on your degrees of freedom, because the t distribution is a known distribution. The t distribution is a series of distributions where the exact shape of each is determined by its respective degrees of freedom. And degrees of freedom represent the numbers of scores that are free to vary in calculating each statistic. One way we can calculate the degrees of freedom by subtracting one from the number of observations in each sample. There are other degrees of freedom, degrees of freedom for the variables if you have multivariate statistical tests and all that, but for this context that we are talking about now is just the one subtracted from the number of observations, right? To perform a t-test, you need to, your measurement need to fill some assumptions. First is that your measurements are based in numbers. You can have nominal data or other types of data. You need to have numbers. You need to have interval or ratio or type of measurement. For pair sample t-test, the differences between pair observations should approximate normal distributions. For other types of t-test, the observations themselves need to be normally distributed or need to approximate a normal distribution. You need to do something about outliers. Outliers are really problematic in this type of tests. And one other important assumption is the homogeneity of variance, which basically means that the variance, that again, I think it's something that you should learn in previous webinars. So the variance between the two groups, if you have, let's say, independent samples t-test, the variance between two groups, the two samples need to be roughly equal. You can report the effect size there, and because the t-test is not bound, the t-statistic is not bound in any number, you can have any t-statistic. You can convert this into a Pearson's R, which is between -1 to +1, with this formula. In order to see the magnitude of your t-statistic, if you don't trust p-values, if you have, let's say, if some assumptions are not met, and you still want to see the effect of your differences, you can convert a t-statistic into a Pearson's R and see if it's big or if it's small. And you can report t-test by stating the purpose of the t-test, report the sample size of each group, report the mean and standard deviation for each group, report the t-statistics, and its associated degrees of freedom, so people can check you. report the p-value and report an effect size. One effect size is the Pearson's R. Right. Let's do some examples. Let's say I have a measurement which is weight loss after a new weight loss drug. I'm a medical company and I made a new drug that is helping people lose weight. And I give this to some people and I measure how much weight they lost in kilograms after 1 week of administration in 100 randomly selected individuals of all ages. So that's between 18 and 65, half of them are men, half of them are women. Literature says that with diet in 1 week, the average person loses 0.5 kilograms. These are made up data. I don't know if this is true. I have made it up for this webinar. So my population mean, or my mu, as you say in English, this is in Greek letter, so I know how to pronounce it, and it's not mu, but I think in English you call it mu. So mu, it's 0.5 kilogram, and I want to compare it with my group of people that I gave the weight loss medication, right? So my null hypothesis will be that there is no difference between my weight loss drug and the population mean. So my sample mean will be the same as the population. And I make a non-directional hypothesis for this experiment, and I say that my sample mean will be different. I'm not saying it will be greater or smaller. I'm just saying it will be different from my population mean. So this is my null hypothesis, and this is my research hypothesis, my alternative hypothesis, right? And I will test this with one sample t-test. Right, so I have my sample mean with this 1.5 kilograms. So my sample lost 1.5 kilograms after 1 week of medication administration. And I have the literature mean from diet. And I move, and my sample standard deviation is 1.2 kilograms. So there's a lot of variation in my sample. And with these two parameters, I move on to solve this one sample t-test. So this is my sample mean, subtracting from it the population mean. And then I have the standard deviation divided by the square root of my sample, which is 100 individuals. And I get this number and this degrees of freedom. So my t statistic is 8.33, and I have a degree of freedom of 99. So I go back into my one sample t-test critical table. And because I don't have degrees of freedom 99 here, I go to the previous one, which is 95. And I see that my statistic, my t statistic is bigger than this number. So the probability of occurrence is less than, of occurrence of this number due to the null hypothesis is less than 1%. So I say something like the p-value that the t statistic came up due to the null hypothesis is less than 1% or 0.01. Okay, so this is for one sample t-test. And then I have another research question. I want to see if there are any differences between men and women who took the weight loss medication. So I know I have 50 men and 50 women, and the mean of the men is 0.9 kilograms with a standard deviation of 0.8 kilograms. They lost in 1 week. And the females, they have a mean of 1.1 kilograms and a standard deviation of 0.85. Just by looking at these means, we can say that the females lost more weight than men. But is this true for the respective populations? All women are going to lose this weight. So before we launch the medication, we need to know more about our sample means. So we need to use the standard error. And to solve this equation, we need to find the standard error for each group. And we get this, sorry, let's just talk about the null hypothesis and the alternative hypothesis. So my null hypothesis is that the mean of women will be the same as the mean of men. And this will mean that the population means of women and men will be the same. And my alternative hypothesis will be that the mean of women and the mean of men is not the same. Again, this is a non-directional hypothesis with a two-tailed hypothesis. Anyway, if I solve this, I get a t-statistics of 1.25 with degrees of freedom of 49 because both groups have 50 individuals, so 50 minus 1 is 49. And if I go to the critical table for independent samples t-test, this is for two tails, I get 49. I don't have the values 49 here, so I get the previous one. And I see that there is more than 20% chance because 1.2, that is my test statistic. There is more than 20% chance that this test statistic was produced by the null hypothesis. So I cannot reject the null hypothesis here. I accept the null hypothesis. So no difference between the population means of men and women of the population means. Even though the sample means are different, if I take into account the standard error, the probability of having this difference in t-test statistics is more than 5%. That is my alpha level. Is the acceptance rate that I choose for having something, a test statistic observed by chance, right? So there is no difference between men and women in weight loss from my medication. So let's take 10 people from my sample and let's test it for another week. Here I didn't solve it. You can do this at home. But the idea, and this is what I wanted to show you, is that I have here my 10 individuals, and in week 1, they lost this amount of weight in kilograms. And in the second week, they lost this amount of weight in kilograms. And to solve this paired sample t-test, I need to find the differences. This D here is the differences. So these are the differences. And this part of the equation wants me to sum the differences squared because it needs to eliminate negative values if there are any, but I don't have here any negative values. And also here I need the sum of differences squared. And I have these values here. So you can solve this at home and go at the critical table and see if there are any differences between week 1 and week 2 of administering the weight loss medication. So this is all for this lecture.
Perfect. Thank you very much. Dr. Stavros Dragoshis will be with us shortly, and we're going to be going through the questions and answer sessions in terms of any questions that anybody has from the presentation or generally about the topic. So,
yeah, thank you, Sebastian, and thank you everyone for attending the webinar. I read some of your questions here, but I also saw some hands that were raised in different parts of the video. I don't know if Sebastian wants to moderate this. How are we going to just answer the Q&A or?
Yes, if you have questions, please post them in the Q&A. We can't promote anybody to a panelist, so there's no purpose to raising your hand. But if you have a question or anything you wish to communicate with us, just post it in the Q&A. So the first question we have is, will the recording be available to watch again later? Yes, it will be, but it will take about a month before it's put up on the VLE. It will be put up on the VLE, though, edited and accessible at any time.
Mm-hmm.
So now we progress.
Yeah. So the first question was about the accessibility of this video. It will be uploaded on VLE after some editing is made, or I don't know, some technical issues. Second question is topic related. So it says, I have a question. Can you explain what a sampling distribution is and describe its key characteristics such as mean, variance, and shape? Okay, so sampling distribution is the idea that we collect measurements from a sample. So the population of interest, for example, me, I'm a psychologist and my interest is in psychology related matters. Let's say I'm looking at a population which has a disorder such as autism or ADHD, anything like that. The whole population of interest is all the people who are diagnosed with a certain disorder. But it's unlikely, even though steps were made in recent years to have access to more data or bigger data sets and all this stuff, it's unlikely that I will ever have access to the whole population. So I will have access into a sample from that population. And whatever your target group is or whatever your research interest is on, it is likely that you will only collect measurements from a sample of the whole population of interest. But statistics allow us to make inferences about the population, especially parametric statistics, that this is what we are looking at, or my part of the lectures in this series is about t-test and ANOVA, which are both parametric tests, allow you to make inferences about the population from a sample using the symmetric abilities of the normal distribution. This is within the central limit theorem. The central limit theorem makes the formulas that we looked at to work. So when I say you can parameterize how far the sample mean is from the population mean using a standard error formula, for example, we know this works because of the central limit theorem. So we can make population inferences from sample measurement. And the distribution of sample measurements, for example, if I have a frequency distribution, so I want to see how frequently I observed measurements from the sample, that will constitute a sample distribution. If the data follow some characteristics, like if they are normally distributed, I will see a lot of values at the center of the distribution, and these values will taper off as I move away. And this is exactly one of the key things that we looked at the webinar. The mean is it's a central tendency of the distribution. It shows the middle point of the distribution, and the middle point in a normal distribution also suggests that in a frequency distribution shows where the most values are. So most of the values are located at or around the mean. The variance, it's a key term that you need to understand before going into statistics. The variance shows the dispersion of values. It's made from an equation which takes every value and passes it through a process and gives us the dispersion of values in a measurement. The shape now, if we have different distributions, they can have different shapes. They can be skewed. It can be positively or negatively skewed. This is if the most values are not located in the center, and this happens if you have outliers. For example, you can imagine a distribution that is normal. It has a bell-shaped curve, but when I make some measurements from outliers, one of the tails will be stretched because I will have outliers. And this will move the mean. So the mean is affected by outliers, and the middle point will not show us where most of the most values are, the most frequent observations are. The central limit theorem, it's a statistical theorem. It's the central in its name, I've read, shows how important it is. Not that it talks about central tendencies. It's really important. It's a very important theorem that makes the parametric statistics work. It allows us to make inferences about a population from a sample if some assumptions are made. And the way we know that the central limit theorem works in most occasions is that if we collect many small samples and we calculate the mean of them, and then we plot the means, the resulting mean distribution, so the distribution of the different sample means, will be normal even if the sampling distributions are not normal. So as I increase my samples or sample size, I approximate a normal distribution. And this is important because it makes all the formulas to work. The standard, we can use the standard deviation to move through the space to calculate, to integrate to find the proportion of space that we are covering, how far some parameters are from a hypothesized parameter, and generally it makes the formulas work. So that's why it's really important. And really what it makes this it's believable to me is that even if you take a binomial distribution, so if you flip a coin, let's say 10 times, and you observe how many of these coin throws are heads, let's say, and you do this multiple times, even though you start from a binomial distribution, if you plot the means of this, how many times you observe heads or tails, you will end up with a normal distribution. So if you even if you start with something like a binomial distribution and plot and collect many samples from coin throws, you will end up with a normal distribution. So there are many occasions where the central limit theory applies, and the idea that as you increase samples or sample size, you approximate the normal distribution, holds even in peculiar situations like that, where you have a prior binomial distribution and you end up in a posterior normal distribution, if I can say this term. Can you define the t-test and explain the situation in which it's most appropriate use for statistical analysis? Historically, I think the t-test was developed to work with small samples. And you see that if we increase sample, as I show you in the experiment, where in the hypothesized experiment, where I had 100 individuals, so my degrees of freedom were 99 for one sample t-test, even though I had a large standard deviation, which is something that is not ideal, let's say, I got a significant t-test. So it was developed to work with small sample size. But having said that, it's not really there is no any real issue. If you want to compare means, if you want to compare averages, you have this group and the other group. The t-test is a tool in your tool case. So it can be used anytime you want to compare two means. How should the result of a t-test including the how should the result of a t-test including the p-value and the test statistics be interpreted in the context of hypothesis testing? How should the result of a t-test be interpreted? The p-value that is associated with the t statistic shows us the probability of having that t statistic if the null hypothesis was true. So the critical tables that we are going and finding the probability of occurrence of every t statistics, they are made from simulations that show that the null hypothesis is true. So if there is no difference between two averages, having certain degrees of freedom. So these are frequency distributions, and the t distribution is approximately normal, and we get this probability of occurrence. And these t distributions are made when they are made with simulated null hypothesis as being true. So the difference between two means is simulated to be 0. You have some degrees of freedom every time, and we find the probability of no difference between two means, let's say, producing a t statistic. And sometimes the t statistic is produced. And if the t statistic is produced less frequent than our acceptance rate, our alpha level, then we reject the null hypothesis, because there is a small chance that our statistic was produced if the null hypothesis was true. So the p-value shows us the probability that a t statistic is produced if a null hypothesis is true. If the p-value is less than our acceptance level, then we reject the null hypothesis. we say there's a small chance that this difference in means was produced by the null hypothesis. So the alternative hypothesis might have produced it. But the way the null hypothesis significance testing is working is that we only reject or accept the null hypothesis. So we say that we reject the null hypothesis if the p-value of that is associated with a certain t-statistic is less than our acceptance rate. So I hope that I have answered to AM3's.
Better if we don't say the names, Dr. Stavros.
Oh, sorry.
We don't say students' names, but I think it was a very thorough and complete answer. We've now got another very long question. You could probably do it in the same way as the previous one. Are the assumptions for Pearson's correlation test and t-test still relevant for census method? Assumptions needed to be made are: 1, dependent and independent variables must be measured at the interval or ratio level, resulting in continuous data. 2, linear relationship needs to be established between the two variables. 3, the non-existence of notable outliers, since outliers have an excessive effect on the value of R, stipulates normal distribution. 4, 5, homoscedasticity. 6, homogeneity of variance. So it's another involved question. I leave it to you, Dr. Stavros.
Thank you, Sebastian. I'm not in any way an expert on census methods. I've never even came across census data myself, but my understanding is that census tries to cover the whole population, so there's no need for parametric or any other inferential statistics. So I'm not sure. So my understanding of census data is that you just show percentages, and if you cover the population, that should be convincing. But I'm in no way expert in census. So that's more like my understanding, but I can't really tell you if Pearson's and t-test are really something that you would use in a census. No, something happened. Right. Oh no, it's okay. I found it. Second, so are relevant for census? So I don't know about the assumptions if these are relevant for census method. I don't really know that. And then you go dependent and independent variables must be measured at the interval or ratio level, resulting in continuous data. That's correct. That's correct for both these tests, even though this webinar is about t-test and not about Pearson's R.
Okay.
Linear relationship needs to be established between the two variables. I think Pearson's R is trying to establish linear relationship. So if you can establish linear relationships from before, why? It's not an assumption to establish linear relationships. Rather, it is an assumption to have linearity, as we discussed in the ANOVA video, which is the idea that a linear model can be used, and this exists for t-test.
Okay.
The non-existence of notable outliers, since outliers have an excessive effect on the value of R. Well, outliers are problematic in many occasions, but more so in the t-test, because the t-tests are trying to find the difference between means. And if you have a mean that is pulled down or up because of an outlier, then the difference of the means will also be problematic or far from the truth. Outliers are a big issue, and it would be nice if there was a webinar on the methods and ideas behind treating outliers, because it's not always so straightforward. Sometimes we just look, we transform the data into z-scores, and we say whatever is 3 standard deviation above the mean or 2 standard deviation above the mean, we delete it. But this is not always something that you want to do. It's really a big topic, how to treat outliers, and outliers are always problematic, especially in the theoretical part of research. If you observe outliers, these are still your data, and if you remove outliers, you still need to report it. So there is some things that you need to take into consideration. Stipulates normal distribution. We need to have normal distributions for each group in the t-test, and in Pearson's R, for the 2 variables, we do need to have a normal distribution for each variable. Here I want to say something that it wasn't clear before. Is for a t-test, we have one variable that is measured on an interval or a ratio scale, but the other, of course, is a binary variable, because you have a variable with 2 levels, 2 groups. So
shall we move ahead? Sorry.
Yeah.
So shall we get ahead with the other questions, because we've only got 10 minutes left?
Yeah, sure. Just one last one here. Homoscedasticity and homogeneity of variance are the same thing, and we need to have homogeneity of variance between the groups. Variances need to be equal or assumed to be equal. But SPSS produces 2 statistics, one with assumes that equal variances exist, and one that does not assume that and corrects for the degrees of freedom. This is also called the Welsh t-test, I think. Greetings, is it possible to increase the audio? Yes, audio was low. I don't know if they can edit this to make it better.
So shall we get to the next questions about the presentation? How useful is this to mixed method research dissertation?
How useful if?
How useful is this to mixed method research dissertation?
It's always a good idea to use mixed methods, but again, this depends on the research question. You really need to take into consideration many things when you are doing your dissertation. You need to take into consideration time, money, if maybe you need to get access to some questionnaires, or if you are going to give monetary reward to participants and all this stuff, and whether you really need to combine qualitative and quantitative methodologies, if this helps your research question, and this will come up from your literature review.
Okay, nice. Next question. What is the difference between normal distribution and standard normal distribution?
Well, the normal distribution is a distribution of raw values. So the distribution of the values that you've measured, and the standard normal distribution is a distribution of the z-score of your variable. So the standard normal distribution has a mean of 0 and a standard deviation of 1.
Excellent. So, in normal distribution, you mentioned that the mean and median can have equal values. Can you please explain how that is possible?
Yes. if you have a perfect normal distribution, all central tendencies will converge. The center will be one thing. You will not have different ways to describe the center of the normal distribution or the peak of the bell-shaped curve. And this will be apparent in all possible central tendencies. That's the mean, the median, and the mode.
Okay. Nice. How can I ensure that I have the right sample size if I am using a mixed methods approach?
Well, that's a really good question. I'm not exactly sure if I can answer this. I don't know a lot about qualitative methodologies, so I don't know how sample size is calculated. That part of your mixed methodology, but for the quantitative part, there is a specific analysis that is done a priori. It's called power analysis, and it's the idea that you want to find a sample size that will give you enough power. Power is another name to say how to avoid type 2 errors. And so you specify the effect that you are looking for, and by using this power analysis method, you can have an idea about the sample size that it is required to get the specified effect. But you can specify an effect with certain statistical analysis. Or if you are planning to do t-test, some types of ANOVA, and generally work with differences, then it's easier to know what sample you want. But if you are doing some other statistics like multi-level statistics or stuff like that, then I don't think there's a method to know the power that you want.
Okay. Can I perform correlation on null hypothesis with p-value?
This question needs to be phrased a little bit different. I don't think the null hypothesis of a correlation, it's that there will be no relationship between the variables, but it's not really a hypothesis test. So then the idea of a null hypothesis doesn't really is not exactly the same in correlation, I think.
Okay. I'm not sure about this question. Are assumptions relevant when the entire population rather than a sample is used?
Sorry. Are assumptions relevant when the entire population rather than a sample is used? In rare occasions where there is access to the whole population, you don't need to have any assumptions because parametric statistics are designed to work with samples. So if we are talking about the statistics that we are discussing here, then we don't need to, or this do not apply to the whole population.
Okay.
Yeah.
Can you provide some recommended resources as references as well?
I don't know how I can give a list to Sebastian to upload with the video.
we couldn't upload a list on the video, but now that's a question that's better asked of their supervisor or their school rather than you. There'll be recommended reading that we've also got on our online resources.
Yeah, so this is textbook material. So any good textbook, and one of the courses that I teach here, the Master of Psychology has a module that is related with research methods and statistics, and the references inside that exist in the databases of Unicode, and talk about some of the things that I showed in this webinar, so we can get references from that as well. It's not any special references that I used, it's just textbook material about statistics.
What is the relationship between the R value and the P value in correlation studies?
With the relationship between the R value, the P value shows the probability that there is no relationship between the two variables. It's again, it's the same idea. It's a critical table, but if I remember correctly, because this is not inside the material that I prepared today, so this is just from memory. The Pearson's R distribution, if we are talking about Pearson's R correlation, is not normally distributed. So something needs to be done to this, like there is a transformation to the R values, and the P value is from another distribution, not the Pearson's R distribution. But these are all from memory, and I don't have any material to show. It's a good question, though. We need to find the answer to this.
Good point. Does it mean that in research one should aim at having a normal distribution? How about if otherwise?
Does it mean that in research one should aim to? Does it mean that in research one should? No, one should aim to have a large sample size that it's correctly collected. The central limit theorem says that even if the sample distribution is not normally distributed, if I have a large enough sample or many samples, I can and then find the mean of these samples, and plot them. The means will have a normal distribution. So even if the sample distribution is non-normal, if I have a large enough sample, I can parameterize or make the statistics work, make these formulas that we are showing work, because of the central limit theorem still applies. So aiming for a large sample size is the best option, but and this is not so. It's easier these days because of the data consortia that exist and all these efforts to bring together large numbers of data and big data sets that are freely available online. If you are designing an experiment and you are allowed from your research question, you should also strive to collect your sample randomly, which is another thing that it is important for parametric statistics to have independent observations. And this can only be achieved by random sampling.
Now, this last question we probably don't have time to answer, and it's not really even relevant to this particular webinar. But it is, can you explain with examples chi-square methods?
Chi-square is statistics that show independence between two variables that are not numbers. If I have labels, if I have nominal data or categories, or and what I can do with them is to count them. So let's say I count in a school 5 different jobs that the mothers of the student are doing. I have 5 different labels and how many times these were observed in my schools. And I can find if there is a dependence between this observation by performing a chi-square test. So the chi-square test is a test that is used when I don't have numbers, when I have labels.
Okay. Thank you very much, Dr. Stavros. That is everything. So I'm going to end the webinar now, and we'll see you all at the next webinar, Seminar 4. Thank you very much.
See you. Bye.
Thanks. Bye-bye. Have a good afternoon. Bye-bye.